Hello, I am Alcione Mora. I'm archive scientist for Gaia, and this is an introduction on advanced usage of the Gaia archive. So this is the welcome page for the Gaia archive. And the first thing that you will see is that we have some tabs on top. If you follow the basic tutorial, you will already know that this is the home page, so the welcome page. Then we can do some queries on the search tab, and we have the help tab. The help opens in a separate tab, and it has lots of resources. In particular, it has tutorials, and one of the tutorials it has is this cluster analysis GUI, which is an analysis on the Pleiades cluster. And it's a toy model. It's a very simplified analysis on the Pleiades. Please don't do that for some serious scientific work, but please follow that if you want to know the mechanics and how the Gaia archive works. So you can follow that yourself. Please do that afterwards if you're interested in getting some in-depth information. So we are in the Gaia archive, and if we are in the simple form, we can type in any object, but now we are typing the Pleiades, so it's been resolved by Sinbad, and we are tracing a 2 degrees radius around the location of the Pleiades given by Sinbad. We are not running the query itself, we are just clicking on Show Query. By doing that, we are being transferred to the ADQL form. We are going to spend most of our time working with the Gaia archive here, because here is where we have full control, where we can do all our queries at will. In the beginning, it might feel too much, but we will try to explain the different pieces one by one. So on the left hand, you have a list of tables. Here we have Gaia source, which is the main table. If we click on any of the tables, we will get some information out of it, including the name, and most important, the size of this table. Gaia Data Release 1, it's 1.1 billion rows, and even some density maps in some cases, in this case only for Gaia source. If we want to go into the different columns, we can expand the tree view, and then we see all the different columns. If we click on, let's say, source ID, we get more information on the source ID field. In this box in here, this is where we are typing our ADQL query. So what is ADQL? Why is ADQL important for us? Why should we care? So everything that we did in the simple form, doing some queries around UX Orionis, what we were doing in the backend, we're just running queries like this. So ADQL is a language similar to SQL. What it allows us to do is to select data. If you have never used SQL or any of its dialects to interact with a database, it might sound scary in the beginning, but let's try to analyze this cooked query so we can see that it is not that difficult. And in fact, it is very natural how this query is formed. So the first thing that we have is a select, because we can only select data in ADQL. This is the only statement allowed in ADQL from syntax. Then we have a limit. There is a hard limit on 500 records. This comes from the simple form, but we can remove it in ADQL form. In fact, this is what we will do. Then we have a list of columns. Remember that we only have some columns selected. And then we are taking those columns from one table. The table where we are going to get those data is Gaia source. And then the important thing, the magic, where your knowledge as a scientist comes, is the conditions. We have a where clause, and there what we have is a geometrical condition. So we have a geometrical condition on of a cone search of 2 degrees around some coordinates, which are the location of the Pleiades, and we are looking for points which are taken as well from Gaia. That's everything that you need to know to do your first ADQL query. So if we remove those top 500 limit and we select all columns, so select star, we are getting everything in that region that we have defined. Please note, select star is something to be done with care, because if you do just select star from Gaia source, it will try to give you everything from the Gaia catalog, which is simply too much, and your query will fail eventually. So if now we click on Submit Query, you see we have a spinning wheel showing that something is happening. So we are retrieving data from the archive. So we have indeed retrieved 98,000 rows, and we have two icons in here, one with of a hard disk, one with an arrow pointing down. So download, if we click in here, we can download our job results. And we have a great stuff which has an arrow pointing up. It is great because this means that you can create your own tables out of this job. Not even just from jobs, you can create a user table from any table that you have, even from a table in Visir, but you see, we are not logged in. That's why we cannot do it. So the first thing we need to do is to sign in. Please register as new users if you have not. If we sign in and we add our credentials here, those are mine. Now we see that we are logged in. So this is my name here. Here are my quotas in terms of user tables that I'm allowed to upload to the archive, the jobs that I'm allowed to retrieve, and then some timeout for the queries. The queries just simply die when they take too long to execute. This is something you need to take into account when designing them. So if we go to search and we do exactly what we were doing before, so Pleiades, we are searching Gaia source, 2 degrees. We are showing the query. We submit the query and remove the top 500 and column selection. So select star. And we know that we will retrieve around 100,000 elements. So if we collapse this tree in here, we see that we have something called user tables that we didn't have before. This is because we are logged in. Those are a list of tables that I have used in the past. And in particular, you see some tables that I used for a previous tutorial. So we are going to delete them. We are deleting those tables. So when we delete them, they disappear from the interface. And now we are going to upload the results of this job. And we are going to call it M45 for the Pleiades. So now we have created a table in here. So here we have user Mora M45. We click on show first 20 rows. We see the table, we see the first 20 rows of the table, and you may say, hey, this is not different than showing the results from the job. Well, it is, because the job, it is a job. You cannot do any further filtering on the job, but the table, we can really refine, and this is what we are going to do right now. But the first thing we are going to do is to download the results. So we are going to download the results and save that in an archive. So M45 VO XML VO table. We can represent the proper motion in right ascension and declination of those 2 degrees around the Pleiades. And what we see is that we have 2 distinct populations in here. We have a loose agglomeration of objects for which the proper motion is low, so close to 0, and some well-defined part in the parameter space which seems distinct and has a proper motion different from 0. Of course, those are the Pleiades. We know they are there, and we are looking for them. So this is how they show up, with a different and distinct proper motion. So the next thing that we are going to do is to filter good data. So we are going to select only those stars for which the proper motion over its error is larger than 10. So what we are doing is a bias. This bias is something that you don't want to do in principle for any serious analysis. So please don't do it at home blindly. Do only when you really know what you're doing, but it will allow us to show some nice features of ADQL. So if here instead of username, I put Mora and I submit the query, what has happened? I have retrieved a new job. The new job has 200 rows. And what we have done is to add restrictions. So we are using this table that we have just created. So it works like any other table in the archive. But we are just selecting non-nulls proper motions, also different from 0. And we are computing the ratio between the error and those proper motions. And we are selecting those with a signal-to-noise ratio larger than 10. Remember, this is a bias. This is convenient for showing the ADQL features, but this is something you really need to do with care if you really are interested in deriving average quantities of a given association of stars. So we can retrieve this job. So we are going to save it. You can also send it directly to TopCat via SAM, but now we are saving it. So we are calling it M45 PM filter. Well, if we load this new table, so M45 PM filter, now we can overplot this new table on top of the previous one. If we do some zooming, now we see that the new sample is in blue and it overplots on top of the previous one, but we have the cluster of the Pleiades. It shows very clearly because it's close and the proper motions are very well defined. But most of the field stars, they disappear because they are really very far away and the proper motions, they are not that good. But still, we have some field stars for which the proper motions are well defined. So the next thing we want to do is to do some box in this parameter space in proper motion to select further those stars. For that, what we need to do is to upload the intermediate results we have here into another table. We will do that. We will call it M45 PM filter. It took much less because it's a smaller table, and we see here in user tables that we have it here, M45 PM filter. It only has the 218 rows that we have obtained right now. And if we click on the next query, you need to put your username, in this case, Mora. If you click in here, then you have 106 rows because we have done a much careful filter. And note that we have done that just using this where condition, and we have used some between. So the proper motion in rate ascension is between 15 and 25 milliseconds per year, and in declination it's between -55 and -40 milliseconds per year. So we could download those results or send them directly to TopCat. If we open them and we overplot them, this is not what we want to plot. We want to plot proper motion in right ascension and declination. And here we are. Now we have this green selection, which is exactly as the blue selection, but we have just done a box search around our objects of interest. So in principle, with that, we would be done, because this is what the archive is for. The archive is not to give you final scientific answers. The archive is there to give you some careful selection of stars for analysis afterwards. In this case, from the for the larger than 1 billion initial catalog, we have obtained a sample of 100 objects. 100 objects is something that you really want to analyze in detail, and you want to correlate with additional data, let's say photometry, let's say spectroscopy that you have at hand, to do a more careful analysis than just this rough analysis. But the good thing is that now you don't need to get the full catalog just to get those 100 stars. So this is why this ADQL interface is there to allow you to do complex selections. And how can it help you? Yes, you need to learn ADQL, but ADQL is not really that difficult. One very nice resource is the ADQL cookbook. So first thing that you can do is to go to the archive help and go to ADQL syntax. And here we have a reference to the ADQL cookbook. So the ADQL cookbook has been created by our DPAC colleagues in the United Kingdom, and it provides a very, from the beginning, introduction to the ADQL using Gaia examples. So please start here if you want to know the syntax. And if you want more resources, there are yet more resources. There are also some resources by our German colleagues in the Virtual Observatory. One very interesting resource is the reference card. So if we click in the reference card, this is a reference card that fits, you can print in 2 pages. So in just one piece of paper, you have almost everything you need to know about ADQL. And the important thing is, even if we said that before, this is the syntax of ADQL. Select some columns, some limits from some table, and you put some conditions. You can optionally do some averaging if you want to do some histograms. You can order the results by any real column or any synthetic column that you compute on the fly. And this is it. It's not that much. In one afternoon or one morning that you devote to this, you will start doing some nice ADQL queries. If you mess up, which is part of learning, you can always retrieve your old failed and good queries just clicking here. So the queries are remembered. If you're logged in, they kept there forever because you typically spend some time creating the queries. You don't want to lose them, and you don't if you are logged in because they are there for you until you just erase them. And finally, this is not something that we included in the Gaia archive just to make life miserable for users. This is the standard thing that you will find when interacting with large amounts of data. There is a CDS interface for interacting with the large collection of astronomical catalogs in Strasbourg, and it uses ADQL syntax as well. There are many TAP servers around the world. TAP is the technology behind the Gaia archive. Many of the Gaia archive mirrors, they use TAP, and they use ADQL as well. Not only for the Gaia catalog, but for other catalogs. If you're interested in Sloan data, they have an SQL interface. So even if the syntax is not 100% the same, it's 98% similar. So the effort you will spend here, it will pay off if you want to use Sloan data or even LSST data in the future. So I hope you have enjoyed. I hope you are eager to use the Gaia archive functionality and have good fun using it. That's all. Thank you.